Hi, I'm Antonio Sala. In this video, we are going to pose the differential equation governing this inductor plus resistor serial circuit. We'll do it in an idealized linear case, no magnetic saturation. And then we'll solve it and we'll explore, based on that solution, the steady-state sinusoidal regime and also the initial overcurrents, inrush current that may happen when energizing an inductor. The engineering application of this analysis is, let's say, when you are energizing, let's say, a big transformer from zero current, so you may have overcurrents there, and those overcurrents may be even exacerbated by saturation, as we see in this scope. But okay, the nonlinear part will be discussed in a later video, and also I'll provide a link to the YouTube video I just showed. But okay, let us start with, the easy stuff, linear differential equations and its solution. We will delve into the details with Matlab code, but in the link you have in the description, you will have access to also Matplotlib, NumPy, SymPy, and the like. The same plots as we will see in Matlab, but in Python. Okay, but let's go on with Matlab. So, if we have this circuit, we'll have 1.5 ohm resistor and an inductance of 1 Henry. Okay, so the differential equation of this circuit is that, well, this will be the voltage drop across the inductor, the input voltage minus the voltage drop in the resistor, and the fundamental coil equation tells me that voltage drop divided by inductance is the time derivative of the current. So, replacing these parameters, we will have the differential equation, and in systems and control, we usually wish to express linear equations in this way, and in this case, this will be A, this will be B, this will be the input, the current will be the state, and this will be the normalized way of writing the equation, but it's just, cosmetic in this case. So now we'll replace numerical values and solve it, and well, in later plots we'll simulate 2.2 seconds, let's say. So I will define time as a symbolic variable, current will be defined as a symbolic function of time. We will discuss 50 Hz alternating current examples, and our input voltage waveform will be just the sinusoidal, a peak voltage of 120 volts and sinusoidal of 100 pi, plus an initial phase that for the moment being we'll set to 0 and we'll play with it later on. So this is V of t, the input voltage, and to solve this equation, well, I can just tell the symbolic toolbox of Matlab to solve for it. The derivative of the current equal to V minus R times current divided by inductance with the initial condition of 0 current, which will be, energizing a previously disconnected transformer. So the result is this stuff, which, okay, if we replace pi by its numerical value, we get this solution down here. Okay, I used the symbolic toolbox to solve for it, but okay, if you are, for instance, in a control course or in an electrical engineering course, maybe you are asked to solve this equation by the method of Laplace. So we would transform to S I of S minus I of 0 like this, and then we will solve for I of S, which will be this transfer function times input plus initial condition term, and in our particular case, this is 0, and v of s is the Laplace transform of a sinusoid times the amplitude, and then doing, partial fraction expansion and the like. I leave to you as an exercise to obtain the whole solution, but in here I wish to concentrate in the interpretation of the solution in electrical engineering terms. So as I said, I leave the details for you to complete. Then let us analyze the meaning of this solution. We have two terms. This term is the exponential transient, and this term at the left is the steady state sinusoidal regime, the steady state AC component, which is non-vanishing, and this term is what you will usually compute with impedances and the like. We'll do it in a few minutes. And then this exponential transient will last for a short time, let's say, and will eventually disappear because my system is stable. How long will this exponential transient last? Well, the circuit pole minus R over L is what multiplies the state variable, the current, and then that will be the coefficient of the exponential in the time response. So if I equate this exponential to 0.05, then the solution to that will be the time in which the initial component, let's say exponentially decaying component, well, when time is 0, this exponential takes the value 1, so this 0.38 volts is at 100% presence, and then when this exponential takes the value 0.05, then this component will have lost 95% of its importance, of its contribution to the time response. So if I equate this exponential to 0.05, I numerically solve, I get 1.997. Of course, I can do it with logarithms, and in fact, the settling time is logarithm, natural logarithm of 0.05 divided by the pole, and natural logarithm of 0.05 is roughly minus 3. So this is approximately equal to 3 over the absolute value of this pole. So it's 3 over 1.5, it's 2, that's the settling time. This means that we will have kind of a 2-second transient, and then steady state sinusoidal regime will run forever. Let us plot this current as a function of time to see what it is. And here we have it. We have an exponential decay to something centered around 0, and then we have this mean, which is, exponentially decaying, and in 2 seconds it has lost 95% of its original value. But as you can see, this is the final current amplitude, but we have an initial phase, this one, in which we have the inrush current phenomena, in which roughly we sort of double the initial current than that of the final current predicted by the impedance. And in real transformers, in which we may enter magnetic saturation, this inrush current, instead of being double, can be, let's say, 6 or 10 times larger than that of the final steady state AC. And this takes 2 seconds to vanish, so maybe some fuses may blow in the meantime. So this is something that needs to be analyzed with care in real transformers, but nonlinear simulations of that will be left for a forthcoming video, and the links I will add in the description. So this is the phenomena of the inrush current, and then we will delve a little bit into it by computing an approximation to the initial stages of this response and an approximation to the final stages, which will be the steady state. So let us first consider a particular case with no resistor. If voltage drop at the resistor is negligible, then the derivative of the current is just the input voltage. So if the input voltage is this sinusoidal, then if I start with 0 initial current, the integral of the voltage will be the current, well, divided by L. So if I start at 0, then in the first half voltage is positive, so current will increase, and in the second half voltage is negative, so current will decrease, and after one cycle will be at exactly the same current as we started with, and this will repeat forever. The integral of sine omega t will be minus 1 over omega cosine of omega t plus a constant, and that constant will be this DC component that in the case of not having any resistor losses will remain forever. So if I tell Matlab to compute the formula, I integrate from 0 to t the input voltage waveform divided by L plus initial condition 0, and then I get this expression that, okay, it's the cosine, but with some trigonometric identities. Symbolic toolbox prefers to express it in this way, but I don't mind. The only thing I wish to understand is the plot. So if I plot it superimposed to my prior solution, then here I have in red the no dissipation solution, which has a constant DC component of 0.38 or something like that. And the exponential decay, well, initially starts close to this red curve, but okay, it eventually will decay to being symmetric around the origin. But this no-resistor model somehow predicts that initial inrush, and it is roughly twice the peak than that at the final part of the transient, because the DC component of the red stuff is just in the middle of the sinusoid. So this is the approximation at the starting instance when there is a high inrush current. If we now discuss what happens when a long enough time interval has elapsed, then the steady state sinusoidal regime is computed with the impedance, which is in series the sum of the resistor impedance R plus the inductor impedance L times omega times the imaginary unit J. So this is the impedance, and well, in AC we know that B of omega it's impedance times current. So current is 1 over Z times the input voltage. Then if I multiply the input voltage by 1 over Z, I get a sinusoidal regime in which the modulus of 1 over 7 is the amplitude of the steady state current, which is 0.38 amps, peak to peak current value, and the angle, the argument of this complex number, gives me the phase shift with respect to the input voltage, and that phase shift is almost 90 degrees because at this frequency the power factor is extremely low in this simulation, let's say. So it's basically a purely inductive load. If you compare 1.5 real part to 300 plus imaginary part, real part is nothing, negligible. That's why this angle is close to 90 degrees. So well, after these computations of phase and angle, this sinusoidal in which I add omega t plus the phase of the voltage if non-zero and the extra phase from the impedance computations, then this will be the current. And if I plot it jointly with the full transient stuff, then I get this red plot that, okay, we see that we start with the exponential thing shifted upwards, and then after 2 seconds decaying, more or less, we have reached the final steady state sinusoidal regime. Well, okay, maybe still a bit more, but okay, with a 5% tolerance, let's say, we are already there. If we zoom in, we see that we are getting closer and closer to the steady state sinusoidal in red. Of course, for a mathematician, it will take an infinite amount of time to get there, but okay, for us, 2 seconds is close enough to be within component tolerances. And as we see in the first stages, our inductor current is displaced up so that the peak inrush current is double of that of the steady state AC computations. If this inrush current is a severe problem, we may have a trick for avoiding it. Which is the trick? If we draw the voltage and current waveforms, they are shifted 90 degrees. So if my initial conditions are 0 voltage and 0 current, then somehow I am starting with a different phase, let's say. I am starting in phase. That would be good for a resistive load, but I am starting in a wrong phase compared to the steady state sinusoidal regime, and this is why I get that inrush overcurrent with transients. But if I can time the moment of connection so that the initial current, okay, that's fixed, I cannot change that because my transformer was previously disconnected, but if the phase of the tension wave is the right one to match the 0 crossing point of the current, then I will start spot on the steady state sinusoidal regime. So that's the idea. If my current is delayed 90 degrees, well, 89.7 degrees, then I will need to connect my AC voltage waveform when it is close to its peak, let's say. Indeed, if instead of 0 phase shift of my sinusoidal, I shift the connection instant so that I compensate the current phase shift, then, well, this is complicated for my symbolic toolbox, but okay. This is my new waveform, so I connect my transformer when the mains waveform is, 90 degrees forward from the standard sinusoid. Well, then in that case, if I solve the differential equation, miracle happens and I have no exponential transient, and voila, we are spot on in the sinusoidal steady state with no inrush current, because indeed, if we plot that, here we have steady state sinusoid forever. Transient and steady state coincide, so timing the connection of very large transformers with my power electronics, timing that connection at the right instant may help reduce these overcurrents in the first energization phase of my large transformer. If instead of the exact computation I just delay 90 degrees, half pi radians per second, then we do have exponential transient, but its amplitude of 2 milliamps is way lower than this, almost 400 milliamps. It will be exactly zero if we exactly match the timing of the connection with the power factor stuff, but in a basically inductive load. If we displace things 90 degrees, we start the connection of my inductor when the input waveform is at the maximum, then we are doing this and we are very, very close to the steady state AC sinusoidal regime. So we'll finish with this. In this video, we have shown the differential equation governing this inductor with some resistance in it. In an ideal linear case, magnetic saturation will be left for forthcoming materials, and we saw that we had an initial overcurrent that could be twice the steady state one, and it took 2 seconds to disappear. And this overcurrent is even higher in real transformers, which undergo some sort of saturation. If this is a problem, we showed that timing the connection so that the connection is made at the correct phase to coincide with the zero crossing of the steady state current, then with that timing we could enter spot on the sinusoidal regime and avoid this exponential transient. So with this application of ODE exponentials and the like to this electrical circuit, we end the video. Thanks for watching.